Okay, so a lot of these features of rational function graphs we did talk about in Algebra 2, but we're going to go through them all again now. The characteristics of our graph we can get by looking at zeros of the numerator and zeros of the denominator. So when you can find an x value that makes the denominator 0, but not the numerator, I'm looking up at this top row of the table here. When the denominator is 0, but the numerator is not 0, that gives you vertical asymptotes. So let's say the number 2 makes the denominator 0, then x equals 2 would be a vertical asymptote. Okay, so any number that makes the denominator 0 but not the numerator. And then if we have a number that makes both the numerator and denominator 0, then that creates a hole. And then if we have an x value that makes only the numerator 0 but not the denominator, then that gives us an x-intercept. Okay? So again, you don't need to copy down this next example. It's all there. We're going to go, I would rather you just kind of listen and watch as we go through this, and don't try to write everything down. You'll absorb a lot more of it if you just watch and listen. Okay, so in this first example, we have a function that's a rational function. It's got a numerator and denominator, and it's already factored. And so usually the first thing that's easiest is to look for the common factors in the top and the bottom. So x plus 4 is a common factor in the top and the bottom. What makes that factor 0? X equals -4. And so that's why we have a hole listed at x equals -4. Okay? The other factors do not have common factors in the top, so these two factors are going to give us our vertical asymptotes at 4 and at -1. So we have a hole at -4 and then vertical asymptotes at 4 and -1. And then we look at the numerator for the x-intercepts. So anything that makes the top 0 but not the denominator is going to give us an x-intercept. So we have an x-intercept at 3, 1, and 0. Okay, and we put all those right there as x-intercepts. And then if we want a reference point, if we need more points on our graph, we can just plug in any x value into the original function. In fact, we can even cancel the x plus 4s out, and that'll give us a little bit easier arithmetic. If we cancel out the holes and then plug in values, that'll give us a reference point. So if I plug in 2, for example, it gives me a y value of 1/3, so we could plot the point 2, 1/3, which is shown right there on the graph. Okay, and we could do that with several points if we wanted to get reference points to help us graph it. Okay, and then this one does not have a horizontal asymptote because if we expanded out the top, notice that if we multiplied all the numbers in the top, we'd have, or all the factors that are in the top, we'd have x to the 4th. And if we multiplied all the factors in the bottom, we would have our leading coefficient, or our leading term would be x cubed plus a whole bunch of other stuff. So it's the highest powered terms in the top and the bottom that help us decide if they're, what the end behavior is, if there are horizontal asymptotes or not. And so since the degree of the numerator is higher than the degree of the denominator, if we simplified this, this would just be x, or x over 1. And so as x goes to infinity, we see that this is going to approach infinity as we go to the right. And as x approaches negative infinity, it's going to go to negative infinity as we go to the left. And so there are no horizontal asymptotes because the function is approaching infinity going to the right and negative infinity going to the left. Okay? And now we see all those features in this graph. We see our vertical asymptotes at -1 and 4, there and there. And we see There's a hole marked here. You're not going to see those when you graph in Desmos or on a graphing calculator. That's why it's important that you know how to find the holes algebraically, because those are definitely not going to show up on the graph. The only way you can tell if you want to confirm there's a hole is on the graphing calculator. If you use the trace mode and you type in the x value, like here we know there's a hole at x equals -4. So if I was on my graphing calculator and I typed in x equals -4 in trace mode, it would say y equals, and it would just leave it blank because there's no y value corresponding with that point. Okay, and so we have all of those features graphed. Any questions so far? Okay, in the second example, it's already factored as well. And again, we see that x plus 4 is common to the top and the bottom. So that gives us a hole at x equals -4. The only remaining factor in the bottom is x plus 1, so that tells us there's a vertical asymptote at x equals -1. And then the remaining factor in the top gives us the x-intercept. So 3x is equal to 0 when x equals 0. And that is our x-intercept. Okay, so we see this graph crosses the x-axis at 0. Again, there's a hole at -4, and then to find the matching y value, I didn't show you this in the last problem, but if we want to find the y value for the hole, all we have to do is cancel out the common factor. My function then becomes 3x over x plus 1, and if I plug in 4, that gives me 12 on top, or sorry, what are we plugging in? We're plugging in -4, so that gives me -12 on top and -3 on the bottom, which is +4. So that means my hole is at -4, +4. And again, I can get that by canceling the common factors and plugging in the x-coordinate of the hole, and that'll give me the y-coordinate of the hole as well. Okay? And then in this one, the degree of the numerator, if we multiplied all this out, we'd see that f of x is equal to 3x squared plus 12x, if I expand the top. And if I expand the bottom, that would be x squared plus 5x plus 4. And again, to analyze the end behavior, we really only need to pay attention to the highest degree terms in the top and the bottom. If they're both polynomials, just look at the two highest terms. And this one, we have 3x squared over x squared, so that's the same as 3. So the limit as x approaches infinity of 3x squared plus 12x over x squared plus 5x plus 4 is just equal to 3, because 3x squared over x squared, the x squareds cancel, we just get 3. Okay, so that tells us there's a horizontal asymptote at x equals, or at y equals 3. Horizontal asymptote y equals 3, and we see that on the graph. Alex?
If one of the functions in the denominator or the numerator are not polynomials, you just look at that one function and use that power?
If they're not polynomials, then they can take on completely different shapes. So all of the ones that we're going to be graphing in this particular chapter are going to be polynomials in the top and the bottom. So when we talk about rational functions, we're talking about polynomials in the numerator and denominator. They can get much more complex if they're other types of functions. Okay, any other questions so far? Okay, and then the last part of our discussion is on slant asymptotes, which we did a little bit of that in Algebra 2 as well. A slant asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator. And so if you look at this function that's typed in here, if I multiplied out all the x's, I would have 2x times x times x times x, so that's going to start with 2x to the 4th. And then in the bottom I have x times x times x is x cubed, so we're going to have other stuff added onto that obviously, but we see that the degree of the top is 1 higher than the degree of the bottom. And so what you do then to find the slant asymptote is you do long division, and we'll do that on one of the examples coming up. But we would divide the top by the bottom, and that would give us, if we do the long division, that the answer would look like this expression here. And we're interested in the linear part. Okay, so the linear part is just the 2x plus 4. Because what's going to happen to the rest of it, what's going to happen to 12 over x minus 3 as x goes to infinity? It's going to approach 0. It's going to approach 0. So if that part's going to approach 0, then that's why the graph starts to take on the shape of 2x plus 4. Because the rest of that function becomes insignificant. It becomes so small that it's negligible, and the curve will start to resemble the line y equals 2x plus 4. Okay? So again, if the degree of the top is 1 greater than the degree of the bottom, then we have a slant asymptote. And we just do long division and look at the linear part of the answer we get when we do long division. Okay? So I'd like you to go ahead and work in your groups on example 3. Do part A and B. So A is already factored for you, so you're ready to go ahead and start analyzing. B, you're going to need to factor first, and then start looking at what makes the top 0, what makes the bottom 0. Okay, so the first one is already factored, and I think it's easiest to look for the common factors first. So we have common factors in the top and the bottom. That will tell us that there are holes at x equals 2, or just a hole at x equals 2. And then vertical asymptotes are going to be when the denominator is 0, but not the numerator, so that's only at x equals -1. And then the remaining factors on the top tell us the x-intercepts. So x equals 0 and x equals -3 give us the x-intercepts. Okay, so we've analyzed all the factors so far. Now we want to look at, we want to look at the end behavior. Is there a horizontal asymptote or a slant asymptote or neither? And so if we just focus on those highest powered terms in the top and the bottom, we notice that the degree of the top is 1 greater than the degree of the bottom. So that means there's going to be a slant asymptote. So to get the slant asymptote, we have to do long division. X squared minus x minus 2 into x cubed plus x squared minus 6x. That goes in x times. Subtract, and we get 2x squared minus 4x. And then it goes in twice. 2x squared minus 2x minus 4. Subtract, and we get -2x minus 4. Actually, plus 4. That is our remainder, and so that is plus -2x plus 4 over x squared minus x minus 2. Now, as x goes to infinity, this is going to approach 0. So it becomes insignificant. It's the linear part that creates our slant asymptote, because as x approaches infinity or negative infinity, this fraction part becomes insignificant, so the curve f of x starts to act like this. It starts to act like x plus 2, which means it's going to approach a linear function. And so our slant asymptote is y equals x plus 2. So that's where we look. We look at the linear part of the long division quotient to get our slant asymptote, because the fraction part, the rational part, will approach 0 because the denominator has a larger power. Okay, so now we have a lot of the features that we need, and so we can go ahead and try sketching this. So we know there is a vertical asymptote at -1. There's a hole at -1, and we can find its y-coordinate if we look at the original function and we cancel out those common factors and then plug in -1. Look at what we'd get. We'd have -1 times 2. -1 times 2 on top is -2. In the bottom, if we plug in -1... yes, sorry, I was looking in the wrong place. The hole is at 2, so I would plug in 2, and that would give me 2 times 5 over 3, so that is 10/3. So the y value is 10/3. So now we know our hole not only occurs at 2, it occurs at 2 10/3, which is a little bit more than 3. So there's a hole right there. And then, let's see, we also have x-intercepts at 0 and 3, so there's an x-intercept there and an x-intercept there. And there's a slant asymptote, y equals x plus 2. So that is a line that has a y-intercept of 2 and a slope of 1. Oh, this x-intercept was at -3, not +3. X-intercept at -3. Okay, good. All right, so now we have enough detail to be able to sketch this graph, because in order to go through this point at 0, 0 and hit the hole up here, it's going to have to approach the slant asymptote like that, and then going the other direction, it's going to have to approach the vertical asymptote. And then from this point at -3, 0, as we go up, it's going to approach the vertical asymptote, and maybe not so steep because we have to approach this slant asymptote here, so it's going to look more like this and approach. Remember, we have this vertical asymptote here, so it's going to approach the vertical asymptote going up and the slant asymptote going down. Okay? And so then we can compare that with a Desmos graph of the same function, and we see the same features there. We have a vertical asymptote at x equals -1 and a slant asymptote at y equals 2. And so we do see the same thing we saw in our sketch, that it's approaching that slant asymptote as it goes up to the right and down to the left, and it's approaching the green dotted vertical asymptote when x gets close to -1. Okay? Any questions on that example? Okay? And then the second one, first we have to factor. So if we factor out an x from the top, we have x times x minus 4. Factor an x out of the bottom. We have x squared minus 2x minus 3, which can be factored again. The denominator is now going to be x minus 3, x plus 1. And so we have a hole at x equals 0. We have vertical asymptotes when the denominator is 0. So x equals 3, x equals -1. We have an x-intercept when the top is 0, when only the top is 0. X-intercept at 4. And then if we look at the highest powered terms in the top and the bottom has a larger degree, x squared over, so if I'm taking the limit, if I'm taking the limit as x approaches infinity of x squared minus 4x over x cubed minus 2x squared minus 3x, I only really need to look at the highest powered terms, and that starts to look like 1 over x, and x is approaching infinity, so that's going to approach 0. Because as the denominator gets larger, our fraction approaches 0. So the whole function approaches 0, which tells us there's a horizontal asymptote at y equals 0. So if we incorporate all that stuff, vertical asymptote at 3, horizontal asymptote, or another vertical asymptote at -1, a hole at 0 something. So if we cancel the common factors and plug that in, we're going to get 0 minus 4 over 0 minus 3, 0 plus 1, and that is -4 over -3, so 4/3. So our hole is actually at 0, positive 4/3. So 0, 4/3 would be right about there. And then we have an x-intercept at 4. And we don't really have enough other points in order to graph this. We would need to plot a few more points. And what you'd see if you plotted some more points, if you got some more reference points, like if you plug in -2, for example, if you plug in -2 into the original function, or plug it in here, this would be 2 minus 4, 2 minus 3, 2 plus 1, and that is -2 on top, and -3 in the bottom, so 2/3 is positive. And so again, we would probably want to plot some more points, but what you end up with if you start analyzing more points here is the graph approaching its asymptotes here. Remember, we had a horizontal asymptote at y equals 0, which I didn't show, but that would look like this, a horizontal asymptote at y equals 0. So our graph is going to approach that horizontal asymptote, going to the right. In the middle, again, without more details, you wouldn't really know which direction it's going. We will get, in later chapters, we will do more analysis to figure out what's happening near the asymptotes, but that's going to look like that. And then this point, it's kind of interesting. It starts down here, and it comes up above, and then as it goes to the right, it approaches its asymptote. That's the only way that it can go through this x-intercept at 4 and still approach the asymptote, is if it comes back down to it. And so again, we're not focused so much on the graph in this chapter, but I wanted you to show the graph so you understand what all these features mean. But your main focus in this chapter is to find these features and not necessarily be able to reflect them on a graph. If we look at the Desmos graph for this one, it looks like that. And I don't think we marked our hole over here, did we? Oh yeah, I did it. 0 2/3 was our, or 0 4/3 was our hole. So there's the Desmos graph. And again, you don't see the hole, but there would be one at the point 0 4/3. And I'll change that to a hole. So there it is. There's the hole right there on the graph.
I was going to ask, how do you know the Y-for of the hole?
By plugging it in. That's what I did back here. Right up here, I plugged in 0 because we knew the x-coordinate of the hole was 0. So I plugged in 0 into not the original function, but the original function with the common factors canceled. And then that allows us to plug into the remaining factors. So when I plugged in 0, that's where I got the -4 over -3. This should be a 0 as well. So I put in 0 for all the x's, and the y value turned out to be 4/3. Okay, any other questions?
Wait, is it just does the decimals graph is below the x-axis on the...
Oh, you're right. I had that one going the wrong direction. So let's see. Was it supposed to be negative 2/3, or did I plug that in really quickly? So maybe we should do that again. I got 2/3 when I did it. So we have x minus 4. If we plug, I think I plugged in 2, and I meant to plug in negative 2. So it was negative 2 minus 4, negative 2 minus 3, and negative 2 plus 1. So let's try that again. You're right, I had the wrong reference point. So that gave me negative 6, and then in the bottom, what do we get? Negative 5 times negative 1. 5. So we get negative 6/5. So that would be down here. Negative 6/5 would be down here. And so if I had the correct reference point there the first time, then I probably would have had the correct portion of that graph. So you're right. It's because when I plugged in negative 2, I think I actually plugged in positive 2. And so that is correct. Now, thanks for catching that, Golly. Okay, any questions?